So what we're going to do is use the equation that we derived from the lab, so the Ohm's Law lab, and we're going to do some examples using this equation to make sure we know how everything works. So in the lab, we derived this equation, I equals V over R. So here I is current, V is voltage, and R is resistance. So the relationships that we saw, that as the voltage increases, so this part of the equation goes up, that means current will also go up. But as resistance goes up, this part of the equation increases, so the overall current will decrease. So these, I and V, have a direct relationship. R and I have an inverse relationship. So what we can do is take this equation and make it into a form that's a little bit easier to deal with. And so all you have to do is multiply both sides by R, right? Because that's how we get rid of the fraction, is we multiply by the denominator. And we're left with V equals IR, which is right here. V equals IR. So this is the form we're going to use to solve our problems, because this one doesn't have a fraction that we have to deal with. But realize that this one is what tells you those conceptual changes. This one is just easier to do the math. So here we go. Example. The resistance of a steam iron is 19 ohms. So first thing we're going to do is underline one of our givens. So resistance is R. What is the current? Okay, so what is the current? So we're looking for current, which is I, in the iron when it's connected across a potential difference of 120 volts. So volts is V. Remember, that's the only one where that's the case, where the unit and the variable are the same, or the symbol. So our equation, V equals IR. So we're going to plug everything in. We have R, which is 19. We have V, which is 120. And we're looking for I. So to solve for I, we're going to divide both sides by 19. And we are left with I of 6.316. And I is measured in amps. Remember, C, current, CIA. So current is I measured in A, CIA. All right, next example. A typical color television draws 2.5 amps of current. So CIA. When connected across a potential difference of 115 volts. So V and V. What is the effective resistance of the television set? So this time we're looking for R. So V equals IR. We have V, 115. We have I, which is 2.5. And now we're looking for R. So we're going to divide by 2.5. And we get a resistance of 46 ohms. And again, the ohm is an uppercase omega, but as long as it looks kind of like a horseshoe, you're fine. I know what you mean. All right, so here's another example. It says, what would happen to the current if the resistance was doubled? Ooh, there's no number here. But this is a change. Saying doubled, so this is a factor problem. So these last two, 1 and 2, have been plug and chug. Every number has had a unit. This time, we don't have numbers with units, we have changes. So we're going to start with our equation, V equals IR, and we're looking for what would happen to the current. So we're looking for changes in current if the resistance is doubled. So resistance is R. So I is changing because of R. That means V is not. So we're circling I, we're circling R. This is not changing. Anytime you have a blank, you use a 1 as a placeholder. So 1 equals I times resistance, which is doubled. So then we solve for I, and we get 1/2. Plus, we also know that these have an inverse relationship. So if resistance doubles, current should half. Inverses of each other, 2 and 1/2. So current or resistance doubles, current is half of the original. All right, last example. How would the current change? So again, we're looking for how current changes if the voltage doubled. So again, this is a factor problem. There are no values with numbers and units. So voltage is doubling. So we start with V equals IR. So V is changing, I is changing, R is not. So we're going to cross it out. So we're left with V equals I. Voltage doubles, so current will also double. This is a direct relationship. Current and voltage have a direct relationship, so if one increases, the other increases. Voltage doubles, current doubles.